chapter 7 is all about exponential functions. And I know some of you are looking at this saying, we're starting with graphs, Mrs. Sargent. Really? Keep in mind, it's not all graphs in this chapter. Okay? We've got solving equations. We're going to learn something called logarithms. But it's not all graphs. But yes, we are starting off today with graphs. So we're going to talk about what the graph of an exponential function looks like. And then we're going to talk about what kind of situations represent exponential functions and how that works. As we look at A, it's y equals 2 to the x. Thoughts? What does y equals 2 to the x look like? Is that one you know? Definitely not. Okay, my pre-cal kids struggle to know that one. I definitely don't expect you to know what it looks like just walking into things right now. So, if we don't know what a graph looks like, I'm going to suggest an xy chart, aren't I? I'm going to say, okay, let's try some x values and get an idea of what it looks like, and I'll help you kind of fill in the gaps here. So, xy chart. What kind of x's are you thinking? 0 is always good. 1, 2, 3, 4. How high is it going to take us? Okay. I was going to stop at 3. Okay. I like 0, 1, 2, 3. We also need to talk about some negatives on this one. Okay. We do need to talk about some negatives. And so I have my x values listed as -3 up to +3 as the ones that we're going to talk about. Well, at least on this first graph. After the first graph, I'll be honest, I'll probably just do -2 to +2. But just to kind of give us a good idea of what this looks like, I'm going to say -3, -2, -1, 0, 1, 2, 3. Okay. I kind of wrote too big there, I guess. Sorry. What equation are we plugging these x values into? We're going with 2 to the x, right? Now, I don't know about you guys. Can we start easy and work our way to the more difficult type? Yeah. Let's start down here at 3. What do we do with 3? 2 to the third, yes. So 2 to the third means 2 times 2 times 2. Do we agree? 2 times 2 is 4. Times 2 is 8. So I'm going to put an 8 down there. Okay? What about if we plug in 2? 2 to the second, which means 2 times 2, which is 4. What about when you plug in 1? What's 2 to the first? 2, right? What happens when you raise anything to the first? You get itself, right? So 2 to the first is 2. Okay, here's a good one to know. 2 raised to the power of 0. Okay, well, I've got the two common answers, 0 and 1. What's your calculator tell you?
1.
Anything raised to the power of 0 is always 1. Okay? Whether it's 2 to the 0, 3 to the 0, 4 to the 0, -2 to the 0, -5 to the 0. Anything raised to 0 is power of 1. That's a good one to stick in your memory. Now, what happens if you forget it? Did your calculator just help you out there? Yeah, the calculator will tell you it also. Okay. What about 2 to the -1? What about if we do it without the calculator? How do we do 2 to the -1 without the calculator? What does a negative exponent tell us to do? Put it under 1, right? In order to get a negative exponent to become positive, we move it to the denominator. We've done this year. You just have to dig it out of your memory. So 2 to the -1 really becomes 1 over 2 to the first. And 1 over 2 to the first is the same thing as saying 1/2. I heard a 0.5 out there. Is that the same?
Yes.
Yeah, that's a calculated version of the answer. It works. I'm not saying it's wrong. I have to use this opportunity to review how do we do negative exponents because it's so easy to forget. But we have to know how to work negative exponents. Okay. Can you do a power of -2 without the calculator? I'm pushing you guys. Trying not to get you to rely on the calculator. Two to the -2. How do I get rid of the negative exponent? Put it under 1. So this is 1 over 2 squared. And 1 over 2 squared is 1/4. So do you know the next one? One-eighth. Because we're going to be doing, I kind of ran out of room here to write it, it's 2 to the -3rd, which is 1 over 2 to the 3rd. Well, what was 2 to the 3rd? That was 8. So this is 1/8. Notice a connection between the top and the bottom? That will always be true, as long as we're not multiplying by anything else. Okay, let's graph this. Let's graph this and see what we can do. -3, 1/8. So -3 takes me what direction? Left 3. What's 1/8 do? You go up 1/8 of a box. It's really, I don't know, it's hard for me to draw that small here. I really went up too much, honestly, right? But you go up 1/8 of a box. Okay. -2, 1/4. -2 takes me, left 2, 1/4 takes me up 1/4 of a box. So pretty much eyeballing it, it looks the same, doesn't it? But technically it's a teensy bit higher. What about -1, 1/2? Left 1, up 1/2 a box. So a teensy bit higher than the last one. 0, 1. Okay, left to right 0, up 1. 1, 2. Right 1 up 2. 2, 4. Right 2 up 4. 3, 8. Right 3. Up 8. Okay, you guys can see my dots, right? My points.
The tiny ones are hard to see, really big ones.
Okay. I was hoping I picked a bright enough color that they're visible, but
I don't think anything helped that.
nothing helps that. Okay. Well, once I graph it. Okay. Can you kind of see what's going on here? Okay. If we were to continue left farther out into the negatives, what you need to realize is that this graph is getting closer and closer to the x-axis, but it never crosses the x-axis. Technically, I'm going to say it never crosses, it never touches the x-axis. The x-axis is something called an asymptote. I don't know if we've talked about that necessarily in here before or not, but it's never going to cross touch. Then, as it crosses through the y-axis, notice, this is the idea of the exponential function. It's going up. And the bigger these x values go, the quicker it moves up. Okay? So, looks something like that. Notice I carefully tried to draw it so it's not crossing the x-axis. It's not that it's going up from the x-axis either. It's running alongside the x-axis. Notice there are arrows on both ends. It is extending indefinitely both directions. Okay. Questions I can answer on that graph?
Well, they always have like the 1/8, the 1/4, the 1/2.
Like the really small numbers? Yes, there will always be some really small numbers. You'll always have, this is very common, you'll always have a portion of the graph that is getting closer and closer, usually to the x-axis, but some line. We've talked, I don't know that it happens till later, because we are going to do some, I think it's in lesson 2 where we do some transformations, where we're moving our graphs again, like up and down, that type of thing, but, yep. Okay. We ready to try B? Okay, let's try B. Y equals 1/3 to the x. You have a little bit of an idea of how this graph looks, but it's also different, isn't it? So, what am I going to suggest we do? XY chart. Now, because we're using a 3 instead of a 2 as the base, my numbers are going to get bigger quicker. I'm only going to go through them -2 to +2. And majority of the time when I do these exponential functions, that's what I do, is -2 to +2 for my XY chart. So -2, -1, 0, 1, 2. Okay. Do you want me to start down with the positives again? We'll work our way to the negatives. Honestly, it doesn't matter, but I like to go with a little bit more of what seems easier to you guys. What are we plugging these values into? One-third to the x, yes? Now, think about it. If we go down here to the bottom, 1/3 to the second. What does 1/3 raised to the power of 2 mean to you? If we're raising something to the power of 2, you multiply it by itself, yes? So one way to think about this is 1/3 times 1/3. You could also think about it as 1 squared over 3 squared. What is 1/3 times 1/3? 1/9. 1 times 1 over 3 times 3. This is 1/9. So there's those little itty bitty fractions I'm going to have to graph again, aren't they? Yes, there's a decimal number there, but I don't want you in the habit of just going straight for the decimals. I'm trying to get you guys to use your brains and think it through here. Thank you. Okay, what happens when I put in the power of 1? One-third raised to the first is 1/3, because anything raised to the power of 1 is itself. So right here, I'm going to fill in 1, 1/3. What about 0? Anything raised to the power of 0 is 1. Okay. Ready to work the brains?
No.
Come on, we got to work out the brains. Okay, here. Let's think this through. 1/3 to the negative first power, correct? What's a negative exponent tell us to do? Okay, put it under 1 normally, yes? Now, that's if it's a whole number. We're going to take, like on the last one, we had to take 2 and put it under 1 to make it a positive exponent. So basically, we took 2, which is 2 over 1, and we made it 1 over 2. This is already a fraction, which makes it the confusing part, right? Flip it. Okay, because when you go and put 1/3 under 1, 1 divided by 1/3 is just going to become 3. And so this really becomes 3 over 1 to the positive first. In other words, when you have a negative exponent, basically whatever's up top goes to the bottom. Whatever's in the bottom goes on top. You can just take the fraction and flip it. What is 3 over 1 raised to the power of 1? 3, yes, because 3 over 1 is 3. 3 raised to the power of 1 is 3. Now, some of you are saying, oh, my calculator told me that. Well, that's possible if you know how to use a calculator, but again, I want us to understand the connection, how to use our brains on this too. I'm not saying you can't use the calculator, though. Okay. Did you guys try 2? Or negative 2, excuse me. What happens, how do we do 1/3 to the power of negative 2? Take the fraction and flip it. So 1 over 3 becomes 3 over 1 raised to the power of 2. Well, 3 over 1 basically is 3. 3 raised to the power of 2, what's 3 squared? 9. Okay. Have you started graphing this?
Yes, I tried.
It's a similar shape, except it's going to end up reflected, flipped, reversed. So let's look at this. So negative 2, 9 tells me to go left 2, up 9. Negative 1, 3 tells me to go left 1, up 3. 0, 1, left to right 0 and up 1. Here's these little fractions again, right? 1, 1/3. You're moving right 1 and then up 1/3 of a box. So basically, land in that box somewhere, right? Huh?
Why is your negative 1/3 and the negative 2 and 9 on the same line? Did you say negative 1?
That is a really good question that I don't have a good answer for other than the fact I messed up.
I was looking at my graph, I was like, wait, what is going on?
I messed up. That's my answer.
It's okay. I just wanted to make sure that I wasn't.
Nope, thank you. I appreciate it. I'm trying to graph on the screen. I'm off to the side. I don't know. Okay. We get 1, 1/3. Did you graph 2, 1, 9? What are we going to do? We're going to go right 2 and up 1/9. So it's the same shape, isn't it? This is a shape of an exponential graph. So it's the same shape, it's just flipped. This one is going to go up and up and up to the left infinitely. And as it's going to go right, guess what's happening? It gets closer and closer to the x-axis. Officially, never crossing, never touching. Now, don't make it go back up, though. It's not going back up. It's getting closer and closer to the x-axis. Just runs alongside of it. And I get it. It's hard to draw it not touching the x-axis. So I get it if yours is running right alongside the x-axis. But make the effort to make sure it doesn't go below the x-axis, because that is a problem. Okay, questions there?
So does the 1/9 not go up, it stays down? Or?
The what? The 1/9?
Yeah. Because if you did the 1/3, it'd go down and up again?
No, because 1/9 is smaller than 1/3.
Okay, so okay.
Yeah. And if we keep going, the next one would be 1/27. And then whatever the next set of 3 is, 81st. So yeah, it just keeps getting smaller and smaller. Okay. And I guess another way to write this, I know we just graphed it as 1/3 to the x, but sometimes you will see this as y equals 3 to the negative x. And I don't know if that makes it more obvious to you, but remember a negative causes a reflection, right? And that's what this graph did. A negative on the x causes the graph to reflect across the y-axis. Okay? It was just shown as a fraction here. Okay, C. What's different about C? There's a stretch. If we want to use those first semester words, there is a stretch. Okay? We're still going to think in terms of an XY chart. Okay? What X values am I going to encourage you to use? -2, -1, 0, 1, 2. Same thing we've been doing, right? I don't know, do you guys like me starting at the bottom, or you want me to start at the top on this one? Start at the top, go right into that negative, attack it.
Sure.
Okay, now let me ask, what are we plugging into? 2 times 3 to the x. You guys know what I mean when I say we're going to have to think about Aunt Sally in this problem?
Parentheses first.
PIMDAS? Yeah. In other words, we're going to have to, when we do this problem, we have to do our exponents there first before we can multiply by 2. So let's go ahead here, and we're going to do 2 times 3 to the -2. It's so tempting to say, oh, that's 6 to the -2. And then I have to tell you, no, it's not. Exponents first. So this is still 2 times, okay, negative exponent says take it to the denominator. So I'm going to say 1 over 3 squared. Right? Negative exponent says take it to the denominator. So 1 over 3 squared. But 1 over 3 squared is 1/9, right? Because 3 times 3 is 9. So this really is 2 times 1/9. What is 2 times 1/9? 2/9? Because what can you think of 2 as? 2 is the fraction 2 over 1. And so this works out to be 2/9. Now, if you did this on the calculator, 2/9 is 0.2 repeating, I believe. So you've got an equivalent answer, didn't you? Okay, and I'm not saying 0.2 repeating is wrong. It's equivalent. Again, trying to work these brains, trying to make you think, how do I do this? Good? Okay, did you try -1, or are you waiting on me? Two times 3 to the -1. Again, first step has to be exponents, parentheses, exponents, multiply and divide, and subtract. So, 2 times, what do we know about 3 to the -1? What do you do with a negative exponent? Goes to the bottom, right? So that's really 1 over 3 to the first, which is just 1 over 3. So 2 times 1/3, which is 2/3. You can think of it as 2 over 1 again. Stick with me. Now we're going to put 0 in. 2 times 3 to the 0. Step 1 is exponents. What is 3 to the power of 0? 1. Anything raised to the power of 0 is 1. So is my final answer 1? No. It now becomes 2 times 1, which is 2. Did you guys catch that? The whole problem wasn't raised to 0 power, which is why the whole answer is not 1. Got the next part? 2 times 3 to the first. 3 to the first is 3. 2 times 3 is 6. Two times 3 to the second. 3 to the second is 9. 2 times 9 is 18. Sorry, yeah, you have to graph 18. Hey, I just think if we'd gone all the way up to 3, you'd be going way bigger. So I tried to keep it reasonable. Okay, shall we graph this? Now keep in mind, this one is, we called that 2 out front a stretch. Because when you multiply by 2, a number bigger than 1, it's going to stretch it. So let's work on this. Negative 2, 2/9. That means you're going to go left 2 and up 2/9 of a box. So you're barely up above the x-axis, right? Negative 1, 2/3. Left 1 and up 2/3. So you're actually closer going up a whole box than, you're actually over the halfway point of that box, but it's still very small, isn't it? 0, 2. Left to right 0 and up 2. 1, 6. Right 1, up 6. 2, 18. Right 2, up 18. So let's see if that's 10. Up in that ballpark? Okay. Do me a favor. Should 18, when you're graphing something like this, should 18 be right on the edge of the graph? No. Okay. I don't know what other teachers say, but, some teachers might say, okay, don't worry about graphing that. I like graphing here because I think it really shows what's going on. This graph is stretching up. It's really being pulled up. So I like graphing it, but make it approximate. Obviously, am I going to have, am I going to say, oh, yeah, go ahead and graph that 50-something? No, but 18. You just had to count up 8 more boxes. It's doable. Okay, what's happening here? As we go left, this graph is getting closer and closer to the x-axis. Never crossing, never touching the x-axis. As it goes right, notice that went up much quicker this time, didn't it? And that's because of the stretch. Okay. These are exponential functions. And as we talk about exponential functions, these represent growth and decay. Remember talking about growth and decay in science? We've probably talked about it at some point. Okay. This examples A and C, these are examples of exponential growth. Because as time passes, your numbers are going much bigger. B is an example of exponential decay. As time passes, my numbers are getting smaller and smaller and smaller. Okay, and I mention that because that kind of goes along with what we're going to talk about next. We good here? I know graphs may not be your favorite, but I appreciate you following along. Okay, fractions, no fun, okay. You'll like this next section. Okay? You'll like this next section. I'm not saying you're going to like the whole lesson today, but you'll like this, I promise. Give it a chance. So we are looking at the idea of, okay, what is an exponential function? And as we talk about exponential functions, we're talking about that form we were just graphing. Y equals a times b to the x. That's what we were just graphing. And that's when you see that form, you know it's exponential. Kind of like when you see x squared, we know it's a parabola. When you see something raised to the power of x, when x is in the exponent, it's exponential. Now, a is what we call the initial value. It's the starter value, right? When you're working in science, there's always some starting point. That's A. That's that initial value. Also, for reference, this is also known as the y-intercept at times, which will be helpful as we continue in the lesson. So when we talk about A being the initial value, it's also the y-intercept. B is the rate of change. So is this growing by 25%? Is it decaying by 12%? Is it, that B value is going to represent your rate of change. If that B value is greater than 1, then it represents growth. Okay, if you've got 1 point something, that's going to represent growth. It's over 100%. If it's B is less than 1, or notice it says B is between 0 and 1, it's going to represent decay because that's under 100%. And so it is decaying. So you've got growth here, and you've got decay. Now, gosh, my brain is not remembering exactly what all is in the homework. I'll have to look that later, but a couple other things. Domain. I know you don't like to hear those words. We're not going to talk about much today. Domain are the x values. What did you notice about those graphs? How far left and right did they go? They were going all the way, right? They're going all the way left. And even when they're going up, didn't it keep going to the right as it went up?
Yeah.
Yeah. On these exponential graphs, the domain is always going to be all real numbers. Okay? Domain is always going to be all real numbers. I used the word asymptote earlier. Are you guys familiar with asymptotes or not? I can't remember if they've been introduced before this or not. Okay, so I talked about mostly, it was the x-axis and the ones we looked at today. That acts as an asymptote. So, and it says the asymptote is y equals 0. Well, realize when it says y equals 0, that is the same thing as the x-axis. And that asymptote, that is a line that the graph never crosses. Never crosses, never touches. So we're talking about x-axis there. And then range. The range is y greater than 0. So I'm saying the range is positive values. Well, where were all these graphs? They were all above the x-axis, weren't they? And so that's saying that, okay, my range is all positive y values because it's all the values above the x-axis. Okay, so that's just a little bit of information. We'll use it sporadically here. And that kind of goes along with the graphs we just talked about. Look at example 2. Identify each function or situation as an example of exponential growth or decay. And then what is the y-intercept? Okay. So as you look at A, y equals 12 times 0.95 raised to the power of x. Is this an example of exponential growth? Or is this an example of exponential decay?
Growth. Because of the stretch.
Well, how do we tell growth or decay? Growth or decay is based on the rate of change, the B value. Where is B? B is the one with the x. What is my B value here? 0.95. What do you know about 0.95?
Plus less than 0.
More than 0.
More than 0, less than 1.
Okay, less than 1 is what I'm going with here, right? It represents a percent under 100%. Okay, so because this number is between 0 to 1, this is an example of decay. Because that number being raised to the power of x is less than 1, is an example of decay. Now, The other piece we were asked? Y-intercept. I referenced this earlier. Were you listening? Did you write it down? What did I say about y-intercept?
It's the initial value.
Okay, the initial value, the A, is your y-intercept. Now, where is A? A is the number out front, kind of your stretch or shrink. It's that number out front that does not have the power. So in this case, A is 12. So what does that tell me that 12 is? My y-intercept. Now, I'll be honest. I am perfectly fine with you telling me the y-intercept is 12. If I recall correctly, Math Excel wants it as an ordered pair. If you're going up 12 on the y-axis, what is that ordered pair? What? 0, 12. Yes, because you go left to right 0, up 12. So a y-intercept would always be 0, comma, a number. Okay. I am really not sure where our time went today. I didn't feel like I spent that much time on the graphs, but I guess I did. Okay.
Time flies though.
I know. So tomorrow, when I am getting attendance, I will probably ask you guys to work on some of those in that bottom section, see what you can come up with. And then we'll continue on to the back part. Okay? If you have not made up your test, make sure you make arrangements to get that finished with me.